Okay, so in this video, we're going to be talking about using the discriminant to find the number of roots of a quadratic polynomial and finding real and complex zeros. Now, the first thing that we need to understand is the discriminant. And the discriminant is a part of the quadratic formula. This is the quadratic formula, and the discriminant is the part under the square root. So it's b squared minus 4ac. Now, essentially, if the discriminant is less than 0, then the zeros are complex and there are no real solutions. If the discriminant is exactly equal to 0, then there is one real solution and the root is repeated. And so if you factor it, you get a perfect square solution. And if the discriminant is greater than 0, the zeros are real and there are two distinct roots. Now they may be messy roots that, are irrational, but nonetheless, they are real. So let's look at some examples. X squared minus 6x plus 10 is equal to 0. So we're going to calculate the discriminant, which is going to be negative 6 squared plus 4 times 1 times 10, which is going to be 36. Oh, sorry, that's a minus. 36 minus 40, which is equal to negative 4. So this means this polynomial has no real solutions. Both roots are complex. And we could go on then and figure out what x is in terms of its complex roots. This will be negative 6 plus or minus the square root of negative 4, all divided by 2 times 1. And if we simplify this, we're going to get 6 plus or minus the square root of negative 4 is 2i divided by 2, or 3 plus or minus I. So those are our complex roots. Now, if we were to modify this equation slightly, minus 6x plus 9, then when we calculated the discriminant, we would get negative 36, or negative 6 quantity squared, minus 4 times 1 times 9, which would give us 36 minus 36, which would be 0. And this factors as x minus 3 quantity squared. And so x is equal to 3, and it has multiplicity 2. So it's a repeated root. The graph is going to come down to the x-axis and touch it, and then not pass through it. It's going to bounce off and stay, in this case, positive. Now let's look at one more example. 3x squared is equal to 4x minus 6. Now, in this case, you would have to move everything over to one side of the equation in order to identify your A, B, and C. And so now if we calculate our discriminant, we're going to get negative 4 squared minus 4 times 3 times 6, which is going to be 16 minus 4 times 3 times 6 is 72. And so 16 minus 72 is going to be negative 56. So this is also going to produce complex solutions. And we can find the exact value of the complex solutions by finishing our quadratic equation. So for plus and minus the square root of negative 56 divided by our leading a term is 3, so this will be divided by 2 times 3, which is 6. And so square root of 56 has factors of 4 and 14. So we can take a square root of 4 out, and we're left with the square root of 14i divided by 6. And this will simplify a little bit. I can divide a 2 out of 4 and 6 and get 2/3. And I can take the 2 and also cancel with the 6 and get the square root of 14 divided by 3i. And those are my two complex solutions. Now, if I were to change the value of some of these coefficients, I could obtain two distinct real roots. And so typically, the simplest way to get a version where we can do that would be maybe to make the constant negative, and that should help. So let's recalculate our discriminant for this particular example. That's going to give us negative 4 squared minus 4 times 3 times negative 6, 16 minus 4 times 3 times negative 6. It's going to give us 88 instead. And so this is real. And so now we can finish out our equation for plus and minus the square root of 88 divided by 6 is, and 88 has a factor of 4 that I can take out, which is going to leave 2 outside the radical and a 22 under the radical divided by 6. And again, I can simplify a little and get 2/3 plus and minus. The 2 will cancel. The square root of 22 divided by 3. And again, there's no I here, and so the solutions are real. And so I have two distinct real roots. To get integer or at least rational solutions, I would need for the number under the square root to be a perfect square. And that doesn't change the fact that it's real, but that would make it potentially factorable if you had a distinct into like a perfect square under there. You would expect that this would actually be factorable. And if you stare at it for a while, you'll figure out that this is in fact not factorable. That's why we get the square root in the solution.